All right. Let's begin. My name is Mario Juric. I'm faculty at the University of Washington. I work on Rubin Solar System data processing, data products. Thank you for joining, coming to this session to hear more about, well, in general, what we've done with Rubin Solar System, and more specifically, given the DP2 release, about what you can find in DP2. I want to mention that there's been a change in the program. Colin Chandler, who was going to give a presentation on from the Solar System Science Collaboration, wasn't able to come at the last minute. So his presentation is going to be given via Zoom by Meg Schwamp, and she's going to go after me. So I'm going to give the first talk, then Meg, then Jake Carlander. So we've reshuffled the schedule a little bit to accommodate that change. Okay. So for years, if not decades, we've been showing pictures like this of Rubin Observatory being built. And now I'm happy that we can start showing pictures like this of what Rubin has started discovering. So I'm going to lead with the conclusions. This is kind of a cheat sheet into what Rubin's delivered so far with the solar system and where to find different things. We've got about 35,000 discoveries so far, and a lot more to come, and a lot more measurements to come as well. So I want to walk you a little bit through how we do it, and then the initial results and DP2. There's going to be a lot more in the talk after me by Jake. Also, those of you who have been at ACM 2 weeks ago, you may recognize some of the slides, but I promise there'll be some new ones as well. So these were the first discoveries, first asteroid discoveries from Rubin. This is from Rubin First Look. They look beautiful. They moved. They were very easy to find, and they were completely un-LSST-like. Because in reality, when LSST takes an image, takes a few images, we get more something akin to this. We get two observations in each part of the sky in the night, and then we have to figure out that our asteroid is that one dot that moves from point A to point B. This is not actually Rubin data. This is from NASA's Lucy spacecraft, is one of the asteroids that it's going to go and visit. The same thing. So how do we do it? The answer is we do it with algorithms and lots of computing. Rubin's discovery cadence is that we image the sky twice a night, each location. We come back to it. And then at that location, we difference, and we measure sources in difference images. Those sources might be moving from image to image, but we don't actually know which one has moved to which one. So there are lots of different combinations if you only have pairs. So we identify all pairs of sources that could move from one image to the next. These are what we're in the business called tracklets. And we tentatively assume that these belong to the same moving object. So how do we confirm if they do or not? We come back to the same area of the sky in 2 or 3 nights. And then we repeat that. We build tracklets, and then we try to see if any of these match any of the others, and provide for a nice Keplerian orbit solution. And we try to link all these plausible linkable tracklets to ones that where the linkage comes back with an orbit solution that has a low chi-squared. That one we trust, and that's a discovery. That's the one that we submit. As you can imagine, this is quite computationally intensive and complicated in many ways. And the fundamental algorithm, the concept is like this, but the implementation has a lot of years of work and smarts behind it, with all of those people up there mentioned, contributing over time to making it actually work. The actually work part was not obvious. These kinds of algorithms have been tried over the years with varying degrees of success. So we were quite happy with Rubin in February. I think we did it, in February, when we submitted about 25,000 new asteroid linkages from 2+ observation tracklets, and it worked. This really proved that the observatory can find tracklets with this cadence. It was an at-scale validation of tracklet linking. We submitted only high confidence tracklets this time, so 4 nights. We're aiming for only 3-night tracklets in the end, or 3 nights worth of tracklets. And the numbers that you can see on this plot, these are daily submissions to the Minor Planet Center. And then we get to the day when we made our submission. So that kind of gives you an idea of the scale. Our submission had data from over the past few months, but when we're fully operating, this column here is going to be what we observe and send every night. So this was a good test that the community can actually intake that much data all at once. Here's what that data looks like when you put in a file to submit. And the two people who I really want to acknowledge who make all of this possible are Ari Hines, who's built our software for discovery, and Jay Kurlander, who we're going to hear from in a second, who's built the rest of our software for discovery. So they really make all these discoveries happen. And in the Rubin Solar System Enterprise, all of you, when you do your science, you're going to be here. And just remember these two guys down there. Go buy them beers or whatever they like. The outer solar system, it was very challenging actually for us to find objects in the data so far, because in much of commissioning, weather and engineering issues made it hard to run the cadence needed for that linking that I showed you, HelioLink. But in the outer solar system, in spite of that, Jake and Ari still found a whole bunch of objects. But in the outer solar system, it's actually easier to find objects because they move slowly enough that we don't have to necessarily build tracklets in the same night. We can try to find them even without tracklets in the same night. And Matt Holman and Kevin Napier, who are on our solar system commissioning team and our early operations team, wrote a specialized trackletless pipeline called Poindexter to go and try to dig out these outer solar system objects in Rubin data, the ones that we collected, the data that we collected so far. And this was the result. And I remember when Matt sent this plot, we all thought, oh, look at the known objects, and then we found a few of new objects, and he was like, no, it's the other way around. We found for every known object that was out there, we found 2 new ones. So the result is, so far, we've discovered 600 new TNOs from early commissioning data, and you should compare that to about 5,000 that we discovered over the last 30 years or so. But wait, there's more. We have 800 more new TNOs coming, being submitted, I think, as we speak. Ari's working on it. And the vast majority of them are going to be new discoveries. So here's the new plot. They look the way they're supposed to look. It's the same major axis versus eccentricity. And once these are accepted by the MPC, I bet that there are going to be some known objects in there, some objects linked to some very old observations. But I bet we're going to have an order of 1,500 new TNOs discovered by Rubin with essentially less than a year's worth of data. And data taken in engineering time during very challenging weather as well. And that is 25% of the entire population at this point. So it kind of gives you a sense of what we can deliver and what we will be delivering going forward. So thank you, Matt and Kevin, for doing this part. So if you're working on the outer solar system enterprise, then Matt and Kevin are here. And here's an audience participation slide. When Matt sent this plot, this is perihelion versus absolute magnitude. So the higher up you are, the larger you are. Sent this plot and said, look, we discovered a very interesting object up on top. So which object is that? Well, that up there is a object formerly known as a planet called Pluto. It's not a new discovery. We thought it was, but it just so happens that various integrators already have Pluto in there, so they think you've discovered something new. But the more interesting question is, if you know anything about Pluto, you'll know that it's almost visible by the naked eye. So how did we ever see it? Because Rubin saturates at like 14 or 15. Well, the answer is thank you, weather, and thank you, U and Y bands. So this is why we have U band, so we can have a very bright survey of the solar system. So there you go. If you ever wondered what the Pluto looks like in the U band, you can go and grab those images and take a look. But that was fun. For about a microsecond, I was looking at that and thinking, like, is that a planet? Big one? No. Okay, let's talk about data preview 2. And I just want to say I'm going to go through the highlights here and leave most of the details to Jake Kurlander's talk later in the session. You've seen already plots like these. This is the coverage of DP2, and it became available on Monday. This data set is fantastic. Like, I've been staring at the photometry and astrometry and cannot still believe in some ways that it's real. You really should go and download it. It's remarkable if you're used to working with the solar system, especially so because this part here covers the ecliptic. That was the part that we were covering last summer, last Chilean winter, and that's where a lot of these objects are being found. Here's the summary of DP2 tables and the scales involved. In red, I've colored the tables that are of interest to solar system work. So we've got solar system source table. This is where we have solar system specific data for associated to known solar system source. We have solar system object. This is where we're going to find absolute magnitudes in Rubin bands. Then we've got DS source. That is not a solar system specific table. That's why I just underlined. But that's where you're going to find astrometry and photometry for individual solar system sources. And then we have a couple of auxiliary tables from the Minor Planet Center database, including the orbits, number identifications, and current identifications. Those two allow you to, for example, map old provisional designations to numbers and similar. And you're going to see the scales here. There are some tables that are truly gigantic. So force source and force source on the objects are 44 billion and 24 billion rows. Fortunately, we generally don't care about those. Solar system related tables are on order of a few million. So for these, for a lot of the science, it's just going to be, the easiest thing to do is going to be just take the whole thing and load it into data frame and go have fun. This is what those tables look like when you plot them. So over here is the RA deck plot. You see the ecliptic, and it's flipped. Over here is the same plot in the ecliptic coordinates. So you can see that it's centered roughly around 0. This here is a distribution of phase angles. You can see that it's about 20 degrees in width. So there are things on phases between 0 and 20 degrees. But unfortunately, if you look at individual objects, this is for the entire sample for 300,000 objects. But if you take a look at any individual object, they tend to be observed in a very small range of phases, just because of how the telescope observed. It's only one season. Nearly all observations are high elongation observations. This was before twilight observations began. That's what you see in that plot down there. A little bit more. Let's see. Median number of observations per object that you're going to find in DP2 is about 20. So that's this plot. This is the distribution of observation. This is how many objects have a certain number of observations, and median is around 20. But you see that there's a very long tail, and there's a substantial number of objects that have more than 100 observations. These are beautiful if you want to go and study light curves and shapes. So I encourage you to go and look at that. Median observing arc is about 30 days. Again, the distribution is very wide. And most observations, as you're going to see over there, are in R and I bands, then G and Z, and then a little bit in U and Y, Pluto and Pluto. So if we then zoom into that plot, again, on observations per object, about 200,000 objects have more than 10 observations. So that is here. And there's about 7,000 objects that have more than 100 observations. So for these 7, you can probably go and fit periods. Virtually all objects have absolute magnitudes determined in Rubin bands. We've initially tried to fit both an absolute magnitude and the slope. The slope parameter was essentially impossible to fit because of poor phase coverage. So, I'm sorry. So asteroid magnitudes are characterized by 2 numbers, by the absolute magnitude of the asteroid and by what's called a slope parameter that tells you how the magnitude is changing as the viewing angle is changing, or as the phase under which you're looking at the asteroid changes. So it has to, you can think of it as it tells you how much of, let's say, specular reflection-y there is in the asteroid. We had to fix this to a fiducial value of 0.5 to get these fits out. So that's why when you look at these tables, before we fixed it, we were losing many fits due to the fitter trying its best to do the impossible. After we fixed it, nearly all objects have absolute magnitude estimates, and they are pretty good, as you're going to see in a second. Let me talk for a second about data quality. So here's astrometry. Astrometric measurements are repeatable to something like 10 milliarc seconds. So this is a distribution for bright sources. The width of the distribution is an order of 10 milliarc second. So what that means is if you have a very bright asteroid, and if you see offsets for whatever reason that are larger than on order of 10 milliarc seconds, so I shouldn't say offset, scatter for whatever reason it's larger than 10 milliarc second, it's worth looking at. It could be, hypothetically, it could be binary. 10 milliarc seconds is the number that we therefore add in quadrature to the error when reported to the Minor Planet Center. So if you ever look at what we report to the Minor Planet Center and you look at the numbers in our database, you're going to see that the error numbers for error are slightly different. That's because of this addition here to faithfully represent to the Minor Planet Center basically how accurate our astrometry is. To give you a sense of scale, in this work, typically, typical astrometric accuracies are much higher, factor of few than 10 milliarc seconds. So this is going to be remarkably good for astrometric purposes. When we dove a little bit in depth in how in systematics of astrometry, so there's a repeatability of astrometry that is the same object if you reobserve it. What are the measurements, astrometric measurements you're going to get every time you reobserve it. And then there are the systematics. Imagine you observe 1,000 asteroids, you look at their predicted positions, and you ask yourself, how close is the distribution of their measurements to the predicted position? That is what this plot shows. And you look at that median, the median is less than 1 milliarc second. So that essentially tells you that Rubin absolute astrometry is really good. And we're going to hear more about that on Thursday. I think we heard a little bit about that on Monday. This milliarc second precision is what you can expect in terms of systematics. Of course, for each individual measurement, you're going to see scatter, but systematics is good. So this was compared to asteroids that have really long arc of observations and really well-determined orbits. So we were a little bit surprised when we did this for all asteroids, and then found that there seems to be a number of asteroids which have systematic offsets. These here are quasars, and quasars don't, neither do stars. And then we were even more surprised when we plotted that offset as a function of position in the sky. Credit goes to Pietro Bernardinelli, who came up with this plot and the idea to do this. And you can see that there are offsets in order of 20 to 40 milliarc seconds that are less in the north and become more pronounced in the south, and there's some dependence on RA as well. So what we think is going on here is that what we're seeing is an actual offset in orbital. Sorry, what am I trying to say? I think what we're seeing, we suspect that the orbit catalogs have the systematic bias, that this is not something that's coming from Rubin, but we're detecting an actual issue with the orbit catalogs, that the orbit catalogs that we have today are predicting positions, especially when we get down south, that are 20 to 40 milliarc second off relative to where the objects actually are. And the hypothesis is that, first of all, most asteroids are observed from the north, and that doesn't directly strongly constrain the Sutter astrometry. It can wobble a bit. And poor astrometric reference catalogs were fairly common in the south before Gaia. And when we look at where these offsets are most pronounced, they're most pronounced in asteroids discovered in the 2000s and 2010s. And that was before we all adopted Gaia as the reference standard. So it all fits. But now that we have these data published, we can actually go and, or made these data made public, we can actually go and in-depth understand where these offsets are coming from and ultimately help fix this. So it's going to be really nice to look at how the orbits are going to evolve, orbital solutions are going to evolve over the next year or so as Rubin contributes these data to the Minor Planet Center. Photometry. Photometry is also incredibly good for sources. So individual measurements on direct images, so not on difference images. You're going to hear from Eli Rykhoff on Thursday. These are systematic. This is the systematic error floor in millimags for each of the U, G, R, I, Z, Y bands. These are single-digit numbers, and they're low. So this is like 1.1 millimag from the ground. That is fantastic. For DS sources, which is where almost all of the data comes from in DP2, we still haven't characterized these numbers. DS sources do not go through a procedure called FGCM, which Eli is going to talk about on Thursday, which improves these systematics. So it's still really uncharacterized, but we're assuming, or we know that it's better than, it's at least, it's not worse than 10 millimags when it comes to photometry in difference images. So that's what we're using when we report to the Minor Planet Center. If the software returns a formal error less than 10 millimag, we add 10 millimag to everything in Quadrature, so that we guard against let's say too optimistic reports of formal errors. But from your point of view, from the point of view of science, what I'm trying to tell you here is, especially for asteroids that have hundreds of observations, those observations are incredibly precise. So you should be able to go and try to reconstruct light curves, shapes, colors, etc. And then here's an example of that. These are I took 6 asteroids that have the widest range in phase angle, and then fit phase curves onto them. And this is the kind of thing you can see. Each different curve is for different bands, but they look the way you would expect. Okay, let me see. I'm going to start wrapping up soon. So the next thing we have to do is, from our point of view, DP2 is not fully done yet. Now that the data are public, we can go and make it even more public by sending it to the Minor Planet Center. So the first thing that we have on our to-do list is to submit DP2 associations to the Minor Planet Center. Jake will tell you more about it. It'll come in stages. We'll send tracklets first, about 6 million of them, and we'll be submitting them in something like 500,000 large batches starting today. So expect these data to be appearing in the MPC in the next 1 or 2 weeks. We're doing this in phases so that we don't overwhelm them with like one huge 6 million dump. We're also submitting new TNO discoveries. And then I already pointed this out, after this submission, we will discover it's actually more than 1,500, not 1,000, which is about 25% of the entire population. I think it's a reasonably good start. And the last thing, I think Jake will also mention this, is we're working on quantifying the DP2 selection function so that we understand which asteroids have been discovered and which have been missed. All right, so for more information about all of this, wait for about half an hour and you can hear from Jake and then ask us questions. So where do we go next? Next, we have the LSST. LSST has now officially started. This brings much more time devoted to science observing, and it brings a cadence that allows us to build tracklets. Even more importantly, it significantly expands our template coverage. So now we really hope to kick into the high gear. Fortunately, you've heard the bad news about the weather and the catastrophic impacts of it in Chile. So this season, it may be a slower start than we hope, but when we're back, hopefully in September, things will we should start discovering asteroids at a much greater rate. And then, as templates get built up over time, this is what we're moving towards. So this is from a simulation. Once we have full templates, we will have an order of 400,000 observations per night. And for example, in this simulations, we're looking at NEOs. And in here, we have 1,000 NEOs observed in one night. When you do that night over night over night, you get something like this. And this is what we're what we hope to hear about over the next couple of years at this conference and others. These are the numbers, how numbers are going to start changing, numbers of various populations in the solar system, given Rubin's contribution. And as I've already shown you, we're already started to change significantly this TNO number, even though officially the survey started just a couple of weeks ago. But we still have a lot of way to go to get to upping it by a factor of 7 or so, that the simulations are that Joe and Jake did are predicting. All right, to wrap up, the data, what's available and how to get it. If you want to just follow along and get a sense for, at any given time, what Rubin has discovered, look at the list of asteroids, visualize their orbits, and so on, with a little bit more data that we currently have in the kind of publicly oriented tools really good tools that EPO, I want to steal them at some point, that EPO has developed. Use this website. So this is sbx.dirac.dev. If you click on the observatory, you're going to get Rubin by default. You can choose other observatories as well. And this is updated on a nightly basis. This gives you a sense of what we submitted. All of this is clickable. You can go and have fun. If you want to get the actual data that we submitted to the Minor Planet Center, the best place to go to right now is ls.st/ast. That will take you, this is a site organized by the community, by the Asteroid Institute and the Solar System Science Collaboration, where they, on a nightly basis, dump everything from the Minor Planet Center that has been submitted by the Rubin Observatory. You can go and fetch essentially everything we've sent as a nice user-friendly CSV file, and then go do your analyses. If you're looking at things that are happening in real time, I didn't have time to talk about this, but go to the alert brokers. There's a number of them. David Trilling is somewhere. There we go. Talk to David. He's got one specifically for Rubin Solar System Science, so the snaps is awesome. And then go to this website for more detail. And then finally, I think you're going to hear this over and over again this week, but DP2 is out and it's on data.lsst.cloud. So you can go there and all these tables are in there. So that's all I wanted to say here, to give you a brief introduction into what to expect from, or what have we done so far with Rubin Solar System and where to get the data. I think where to get the data is probably the most important thing, because now step 2 is, we're starting to deliver all these data sets, and now you and all of us, we need to get some science out of them. So I hope you're going to join us in doing that. So I'm going to stop here and take a couple of questions. Thank you.
Great talk and exciting science. So we heard in Fed's talk in the previous session that there is a microsurvey in the Twilight Sky. Has that actually started, and how should we think about this in the context of everything else that you told us about?
So it's started, but so a couple of issues. We haven't found anything in that. Well, we haven't reported any NEOs from that survey yet. The reasons are it's ongoing, but it's still limited by the lack of templates. And secondly, it was winter in Chile, so things were not ideal in terms of weather, and now we had really bad weather. So just as that was kicking in, we have these disasters come in. When we're back online, we're going to have the ability to find those trackouts almost in real time. But the challenge for us, for the team, is we need to somehow vet them, because these are the kinds of things where you really, first time you're sending them, you want to make sure that they're real. And I think we are working on some infrastructure to make that easier to do. So that's, now that the data sort of come in, we're going to get that done. But my estimate is like 2 to 3 months until we start submitting regularly trackouts from there.
Thanks, Mario. This is all really great. I did notice comets were conspicuously missing. I was wondering if you could say a few words on where you are with those.
Yeah, sorry about that. So the way our system works, we match against the MPC orbits table that's in the MPC database, and at our cutoff time for this data release, the comets were not in that table yet. And the comments are in the table now. So if a comment were to appear in prompt processing data, we should be able to associate it, assuming that the predicted position of the comet is within 1 arcsecond of where we end up have the detection. All of this has happened recently, just as these bad things started happening down in Chile when it comes to weather. So we don't know how well it works, but if we're missing, when we're back on the sky, if we're missing comets, you should go after us, because now we have no more excuses.
Thanks, Mario. It's Gregory. I'm trying to just put something together. You mentioned there's still work ongoing in submitting DP2 observations to the Minor Planet Center. So there's a set of solar system tables in DP2, right? Do you have like intentions of updating those? Like what state of play do they represent? Like the MPC orbits and SS object tables that were actually released?
So the tables, the SS source tables in DP2 are our observations of known asteroids. So there's asteroids that are already in the Minor Planet Center. So we did not submit those to the Minor Planet Center yet until DP2 became public, because to be honest, their primary, they wouldn't. Long story. Sorry, I can tell you the details we can talk more if there's time. But we've decided to hold it back until things are public. Now that they're public, we're submitting all of that to the Minor Planet Center. The point is, if all the new objects that were in DP2 data, we've already found those even before DP2 was finished and reported it to the Minor Planet Center.
Is the snapshot date of the MPC orbits data in DP2 documented somewhere?
It is March 13. March 13. Yes, it's in the DP2 paper that's going to come out soon. All right, let's take maybe 2 more questions and then move on to Meg, who's going to talk about the collaboration.
Yeah, this is just in response to the comment question, because that came up in the last session as well. That's something I have looked just. We do detect comets with the alert production pipeline, and they even pass a reliability score pretty well because the cores look point source enough, and we don't really see anything about the tail, but they will make it through into the alerts. They already have, and I know that some people are a bit concerned about that because we haven't looked at them very much, but they are there.
I think there was one more question over there.
So as you are able to continue your twilight experiments, might it be possible to keep track of how many tracklet solutions are broken by satellite streaks? That's going to be a really important metric.
I'd have to look into how we could do that. It's not impossible, but it would require some extra work to essentially correlate things that we don't see to an appearance of things that we haven't detected and that we should have detected to an appearance of a satellite trail. It's probably worth doing. But just to give you a sense, we've simulated this and we don't think they're going to be a problem. It's the impact is at a % level. So we should do reasonably well. All right, let me hand it over to Meg Schwamp, who I believe is on Zoom.
Mario, can you hear me?
Yes.
Okay, that's good. We're ahead of schedule. Isn't that exciting? Okay, let's see if this works. Also, please forgive me. It is midnight or just after midnight in my time zone. So if I'm a little punchy, it's just because it's late. And I have a cat staring at me as my audience right now. Okay, so I'm co-chair of the Solar System Science Collaboration with Colin Orion Chandler, who couldn't be there this week as originally planned. And so you get me, Meg Schwamp. So I'm really just talking for the next little while about Prompt Products, DP2, and the Solar System Science Collaboration in sort of the context of what we have in place right now for everyone, and also just to spur your ideas of what things do you feel you need from the collaboration. So I am one of many. So although Colin and I are often at the front, I just want to highlight that these people on this slide, right, are the ones doing a lot of the heavy lifting from our working group leads, or they will be doing the heavy lifting, especially as we ramp up. We have our working group leads. We, based on population and including software and even thinking about technosignatures, we have early career representatives, we have publication coordinators, and then as well as cross science collaborations EDI committee member. So again, I just want to highlight that the collaboration leadership is a group of people, not just the chairs. And so again, to sort of emphasize what Mario has said, there's so much stuff we're going to be able to do with Prompt Products in year one, DP2, the pre-DP2 searches that are in the Minor Planet Center. And just to remind you, this is the figure on the left from the paper by Jake Kurlander that shows TNOs, NEOs, asteroids in their discovery time. And basically, you get most of them in the first few years. So that's really exciting for those populations that we're going to get them early and be able to follow them up as the survey progresses. So just want to remind people that of like our first few years are different than some other science areas. And so I think it's maybe the message to buckle up, right? Given the numbers that Mario is already showing from pre LSST data. Okay, so what is the point of the Solar System Science Collaboration? I think it really is about gathering and connecting the planetary astronomy community. It's linking you all together to do your science. We've been doing that through a series of sprints, so different snapshots over the years, and that we've switched from these preparatory sprints to having our first data sprints in February at Queen's University Belfast. So I want to highlight that, that's that we're now switching modes, right, because of the start of the survey. And again, going from the sort of dark image to the day before the sprint, rainbow over the Lanyon building. But I think I want to highlight that what's coming next is that now that we have DP2, and hopefully by November we will have the images for DP2, I'm hoping, means that in early November, we're planning the second early data sprint in Seattle. That QR code is our registration form. I know many people have been asking me for it. So if you're going to the Spokane DPS, you just need to go a little bit more west afterwards or come in later. And you'll be able to attend in Seattle. And again, we're aware that, various groups want sprints in different locations. And so we're working on thinking about international options, either for this sprint or scheduling another to provide that international option. So our still model right now for these early data sets is to get people together in person, allow online participation. But I'm very eager to hear people's thoughts about how we do that moving forward, especially into 2027. We have funding, thanks to the LSST Discovery Alliance, to do an in-person sprint. Right now, they're thinking of doing it in Canada. We've had some early discussions, but we don't have any dates yet set. But that's the thinking, is to at least be able to do one more sprint that we know will be fully funded. Again, Mario talked about early science Rubin observations. And so I really do want to acknowledge that it was the science collaboration through the community members at the B612 Foundation, the Asteroid Institute, that are scraping the Minor Planet Center so that we can actually access the observations that are within it that are coming from Rubin. That although the Minor Planet Center is public, it's not easy to get that level of observations. They will not let us download them from their API. You have to get a clone of the database. So that if you go to the B612 website, right, you can get access. And we have versions that we've copied up to the RSP that have, right, those observations so that you can use them in tandem with now DP2 and hopefully the Prompt Products that are coming soon. Just want to mention again that we have the Praxis Network. So we set up, or in the process, it should be hopefully finished by the end of next week, a mentoring network. So we have 9 mentees that signed up. We have at least 3 mentoring groups that we'll create. And the idea is that you are either early career, you're new to Rubin, and that you're getting linked with people that have more experience with Rubin data products, the Rubin ecosystem that can help you out. And that it's not just meant for early career. If you're a newbie to Rubin and you're more senior in your career stage, you can also be part of the Praxis Network. And so we'll run this for a year with our 9 and then increase, again, relaunch every year for a new sort of class of mentoring. So this year is going to be an experiment with our 9 mentees, but we're in the process of sort of getting that mentoring group set up. So 3 or 4 possibly that'll be set up in the coming weeks. I want to highlight working groups are becoming more active. So a lot of times we hear that the working groups are pretty quiet. It's because there hasn't been much going on, right? And now the survey is actually started. There is the commissioning data, right? DP2, all the pre-LSST solar system detections. Working groups are becoming more active. You've seen the emails coming out. And so this is only going to continue more and more. And so one of the things that we've heard from feedback is like, how does someone advertise what they're working on, or how do they, sort of ask or highlight that they're looking for collaborators? So the working group leads are adding show and tell or lightning talk session, segments to the working group telecons over the coming months as one way to enable that. I want to also highlight that if you're writing software, we worked with the AAS journals to get a solar system analysis software specifically for Rubin, in mind, focus issue. So you can publish in any of the AAS journals and your article will show up in this focus issue. And so there's now one place you can go see all the public software, right? Open access software that you can use for your LSST analysis. And again, it closes in December 2028. So the idea is that, we've got a few years left, and for people to develop tools now as data starts to arrive. Same thing for predictions. Now that the survey and the cadence are, the survey started, the cadence is much more set. People who want to do predictions, we have a focus issue for that closes in December 2027 because we figure it still needs to be early on in the survey. But again, it's hosted at PSJ, but papers across AAS journals can be included. So if you like AJ, you can still publish in AJ. But I want to highlight that these are 2 opportunities we created as a collaboration for people to do their early science or be able to find the place where all the predictions might be that are coming in the right now as this survey begins. The other thing I just want to highlight is that as a collaboration, one of the things we need to think about in all the ways that we're working are changing, both because of the LSST and the data scale, but also because agentic AI has jumped dramatically. So as a collaboration, we probably need to develop some kind of suggested guidelines of how people should use AI, because not every graduate student or early career or even distinguished member of the collaboration may know or have thought about what are the ethics of using these things and how, can you just take a paper, put it through, ChatGPT and spit out feedback and send that back as your own? Is that okay? And so letting us think about those things and how people should reference when they're using these things, if they're using it to translate code or improve code, et cetera. So it's just, I think, one of the things to highlight that as with LSST, that there's these benefits from being able to use agentic AI that we want to think about how, as a collaboration, we want to use that. And the QR code is to a really great paper by David Hogg that talks about these things. The other thing is that I just want to highlight some other things that are slightly related to year 1, year 2, and just because I have the floor, is that we don't just stop giving feedback on cadence because the LSST has started. There's still discussions about what happens after year 1, or in partly modifications potentially to the tail end of year 1 with this request to support the DESI extended survey by enabling them, I think, to get targets for their to do spectroscopy, by ramping up, doing in these sort of tiers, pushing forward observations. And so thanks to Lynn Jones, who literally plotted this today, you can see the ecliptic as a solid line. The first set of dashed lines are plus minus 10 degrees ecliptic. And then the other larger dashed lines are plus or minus 20. And so a lot of that goes through our area of interest in the wide, fast, deep. And so one of the things we're going to have to, especially thinking about what we get from these early data sets, helping us to inform what we want to say to the Survey Cadence Optimization Committee, the SAOC, about this proposal to push observations into earlier years and then have less in those regions, those banded regions at different points later in the survey. And just to highlight that, Lynn showed this earlier today, and as well as that other slide, there would be less observations in UNG in later years. And I know that that's not great for cometary activity. It's not great for doing color evolution. And so it's something that we will need to emphasize, that showing some of the science that we're able to do with these early data sets. As always, Cadence is always about evenly distributing the unhappiness. So I'm sure that we'll come to there will be some Cadence decisions that will evenly distribute the unhappiness so that DESI gets something and, we get the science that we want to do. But I just want to highlight it that those things aren't done yet. And just the last few things I want to say is that one, there's a co-chair election that's going to be coming this year. It's for my spot. So I am going to run for re-election for one last term if you'll have me. So that's assuming I do a good enough job you want to have me, but we should have a healthy election. And so if you're interested in being co-chair, taking my spot, you should run against me, especially if you think you can do a better job, because we should have healthy competition for co-chairs. So just to say that that's coming up, so you can start thinking about whether you'd be interested in running. You can talk to Colin more when he's back in the office about the role. And then I want to end my time by asking everyone in the room, people online, maybe you can put your name in Slack, that for everybody who is part of the Rubin Observatory Solar System Processing Science Unit, if you can stand up. If you're part of the DM team, stand up. If you've been involved in any part of Rubin commissioning, stand up. If you're in the part of the Minor Planet Center, stand up. And let us all just applaud you and say thank you, because all of you have made us have these discoveries that we're starting to get science from, and we're going to get so much more. And so I just want to end with that, with us actually thanking these folks for all their hard work, because often we see the end product, but we haven't seen the blood, sweat, tears, and lack of sleep to get us there. So let's give them a round of applause and a thank you, and I'll end my time there. So I can't hear anything right now. So I assume there's probably no questions for me, but I'm happy to take questions or feedback about the science collaboration for those that have them. So I don't know if they need to go up to a mic, but or if they have more questions for Mario about
I have a
data products.
I have a quick question until someone raises their hand. You mentioned the AI usage guidelines. Do we have any right now, or do you have some sense like in which direction things are going, or have there been discussions already? Can you give us more detail on that bit?
Yeah, so we currently have none. And I think the way I think things will shake out is that AI is a tool. I think that we'll think of it as your friendly, non-astronomer expert friend, right? And so what things you decide to give to them to do, but right. And so I wouldn't have my, best friend who's an artist or who's a software engineer read through someone's paper and give comments as my own, for example. And so, but if that person helped me significantly programming, I'm definitely going to probably put an acknowledgement somewhere that they helped out, or add them as a co-author, right? And so I think thinking along those lines as a tool, and about how open we are, but that we want to just make sure we have something, because so that someone who's new to the collaboration, or again as someone who hasn't dealt with these tools before, has some guidelines, because I haven't really seen many around. So even I've started to only have these conversations with my own research group recently, as well as if we think about double archive. Now, if somebody has the LLM hallucinated, references, everybody who's on that paper, right, can't can't put articles on archive, right, for a year or something like that. So it's again something to think about, right, there's implications, right, of things. And so just maybe thinking about it as these new tools are there. So I don't think we're going to have anything stern. I think it's going to be a guideline of like, this is what we think you should do, as everything within the science collaboration is. We recommend because the data is available in many forms. So that's the way I would think about it, as more we should have the discussion. And the publication coordinators will be having that.
If I could summarize what I think I just heard you say, your thinking is along the lines, if you use the tool, say you use the tool, and if the tool does something silly, you're still responsible for what the tool did.
Yes, exactly. And be respectful of people's time, so if you're going to do something with it, think about what the other person, the other person that received the output is, like, collating comments or something like that.
One more question for Meg. Going once, twice. All right, let's thank Meg again, and Colin Chandler, who really wanted to be here but couldn't at the last minute. So thanks again, Meg. Okay, so for next and final talk, we have Jake Kurlander, who's a member of our Solar System team at Rubin at the University of Washington. He's going to tell us details of DP2 solar system processing and have questions. We're trying to set aside at least 10 minutes for discussion at the end. So I want to get you all ready to start thinking about what you want to know or what you've poked through the database and you may have found something interesting or confusing. After Jake's talk, ask all of us and we'll try to help you out. All right, Jake, take it away.
Hello, everyone. I'm Jake Kurlander. I'm going to be talking about the Data Preview 2 solar system processing and results. I will be speaking mostly as a member of the Rubin Observatory solar system team, wearing my solar system hat. But at one point, I will take off my observatory hat and speak as a scientist, not representing the observatory. So Data Preview 2 has a couple of solar system specific data sets. This is what we care about. The solar system sources. These are detections of solar system object in a single image. Each solar system source has a corresponding dia source. These are detections in difference images. And then we've got solar system objects. These are minor planet center orbits that we have seen at least once, which there exists at least one solar system source. The precursors here are dia sources and MPC orbits, not produced by us, but very important for the rest of this talk. So I'm going to be talking about the association of dia sources to solar system objects, and then the Rubin fitting of per object parameters from our data. We're done for DP2 to create those two data sets. Rubin Observatory's Data Preview 2 does not explicitly include object discovery. There isn't a part of the DP2 pipelines that discovers objects, but obviously that's very important for this work. So before we talk about the pipelines themselves, we'll talk about the pre-Data Preview 2 discovery runs and the work that was put in to find new asteroids in pre-DP2 data. And then we'll talk about how you can access the data and do science with it. First, the transient catalogs that we created because we didn't have difference images before DP2 ran, then the discovery runs itself, then the pipelines and data sets for DP2, and we'll dig into the data with some plots and access. First, the transient catalogs. So Rubin has promised for a very long time that it's going to discover asteroids with just 2 repeat visits to the same part of the sky each night. And as Mario showed, in order to turn these low confidence 2 detection tracklets into high confidence orbits, we need to see these objects on at least 3 nights, with 2 or more detections. Now, assuming we have really good difference imaging, we don't have too many extra sources sitting around, the false positive rate on 6 detections in a curve can be pretty low. But if the background rate of sources, background density of sources is sufficiently high, it becomes very, very easy to find curves that 6 or more points lie on. So this is a DP2 difference image. Looks nice and clean. There aren't too many extra dots. But before DP2 actually ran, we only had direct images that look like this. Lots of stars, lots of galaxies, and it is very easy to draw a curve that fits 6 points, any 6 points, even if they're stars, in these images. So how did we discover asteroids in the Rubin discovery paradigm before DP2 without difference images that get rid of these stars and static sources? Instead of subtracting images using the templates that data release processing creates, instead we subtracted catalogs. So using the nightly validation catalogs, which are an intermediate data product that hopefully most science folks here don't ever have to think about, we built up maps of the night sky of stationary objects. These are stars and galaxies that sit in the same place, and definitely at least 2 detections on at least 2 nights, but when possible, at least 3 detections on at least 3 nights. There are all sorts of reasons that nightly validation data is less preferable to data releases, but using it in this context is really, really good. We have a few extra steps after building up these stationary star maps and subtracting the stationary stars out of the source catalogs. A lot of artifacts are left over, so we remove them with a series of different density-based cuts. And Matt Holman and Kevin Napier at Harvard did a substantial majority of this work, creating a much, much reduced source density for us to search through for asteroids. We then searched through the reduced catalogs for asteroids, primarily using HelioLink, the Rubin Observatory's asteroid discovery algorithm. We used a 14-night rolling window, so gather up the last 14 nights worth of data. We make tracklets. We look for a couple of detections that are close to each other that could plausibly be one moving object between frames. We assert a whole bunch of distances and the derivatives of distance, hoping that we have correctly guessed the orbit that this asteroid is on. If you propagate tracklets forward, the real objects cluster together in nice tight clumps, and we can find lots of asteroids. Doing this is surprisingly quick. It only requires a few thousand guesses for the main belt, a few tens of thousands of guesses to cover the near Earth object space. And running this on the transient catalogs produced by Matt and Kevin, we found 60,000 candidate asteroids in the pre-DP2 direct image catalogs. There was additionally a very similar algorithm which also asserts a few missing parameters, but instead of asserting these on tracklets, it asserts them on individual detections. So Matt and Kevin searched the outer solar system, the very slow-moving objects, using a tracklet-less algorithm that shows substantially higher completeness in this case. All right, so we've got a whole bunch of candidates, but they came from these less preferable catalogs. How confident are we that these are all real objects? So these false linkages can either be linkages of noise or mixtures of real objects. So that first case image, just a curve through 6 random points, a linkage of noise. These should go away as we reduce the density of sources in our images. But you can also imagine a chance alignment of a couple of asteroids that happens to look really, really good. And if there's a bit of astrometric scatter in your image, you might imagine that one tracklet from one object ends up linked together with 2 tracklets from another object. And this will just happen sometimes independent of how good our catalogs are. It's just a function of the number of asteroids that are on the sky and the astrometric scatter in our images. We found that among 3-nighters, if we didn't make any cuts, we had an impurity rate of about 1 in 500. That is, about 1 in 500 of the asteroids we discovered were not individual real asteroids. There were a couple of asteroids mixed together, or one asteroid mixed together with some non-asteroidal sources. But Ari Hines put in a tremendous amount of work into looking at different cuts we could make on our observables, trying to find a very, very pure region of this parameter space, trying to preserve our ability to discover new asteroids on just 3 nights of 2 detections each. And his favorite cut is that if a 3-nighter is found with a time span of less than 12 days and an RMS magnitude, assuming normal asteroidal colors, less than 0.45 magnitudes, then our 1 in 500 rate of fake asteroids drops down to 1 in 10,000, which is really, really good. And these cuts include most of the 3-night asteroids that we found. 4-nighters are pretty much always safe, pretty much never mixtures. And if we make these cuts, which are the cuts that we made for pre-DP2 discovery submission, then we can maintain very high purity and submit almost everything. The asterisk here is that this does assume mean asteroid colors, and if an object is particularly variable, as a whole bunch of interesting objects like Oumuamua are, this might exclude them, so we might have some biases with respect to things that people care about, but this is so much better than the other solutions. It lets us find a ton of objects, works very well. All right, so we had something like 60,000 candidates. We submit them to the Minor Planet Center. A whole bunch of these ended up being known objects with substantial ephemeris uncertainty, or allowed the Minor Planet Center to fit in orbit, but another observatory got discovery credit because they had some earlier tracklets. 11,000 of our 60-ish thousand candidates ended up as new discoveries credited to Rubin. These went into the Minor Planet Center. We pulled them down on March 13th, associated them in DP2 to known objects. But once the DP2 DIA sources were created, we also went through, again, and searched those DIA sources with these same algorithms. And in that search, we found an additional 20,000 asteroids. So these 20,000 asteroids found in the Rubin DP2 DIA sources are not included in the SS object or the Minor Planet Center table for DP2. And if you search DP2 for new objects, you will find these 20,000 asteroids, which have already been submitted to the Minor Planet Center, just not labeled in DP2. This is something that has to happen because of the timing of the pipelines. But we're up to something like 35,000 new objects from Rubin now. All right, the pipelines themselves. How do we associate known objects to sources and fit per object parameters? So we start with the Minor Planet Center orbits catalog. We restrict these to objects with at least 3 days because there are some really bad orbits from the early 2010s that have 1 or 2 days of arc that just crash into the Earth and kill your integrator. So for all the orbits known by the Minor Planet Center, which have arcs of at least 3 days, we propagate their nominal positions forward into the position of every DP2 frame. We do this using a tool called SORCA. It's a survey simulator that does a whole lot more than ephemeris generation, but it also does really efficient ephemeris generation if you're an observer. Really, really good. We aren't propagating any orbital uncertainties at the moment. We're doing on-sky uncertainty matching. So take associations of objects with high ephemeris uncertainty with a grain of salt. It's not a guarantee that an SS source is really that SS source. And we're going to talk a bit more about how to filter down to really high confidence SS sources. So once we've got our ephemeres for each DP2 visit, the DIA sources from that visit get cross-matched against our ephemerides. We do this again as a 1 arcsecond matching radius with no probability, no ephemeris uncertainty. And so you will likely want to filter these down to associations that you really believe, but almost all of these are very, very believable. Here is one known fast-moving NEO. I think that's 1999 MN or something. It is a streak-looking thing, but the Rubin pipelines very happily make a DIA source whose center lies right at the center of that streak. We've got a 1 arcsecond circle around the ephemeris position of this asteroid drawn on there. And because those two match, an SS source is created. This is the orbit information from the ephemeris that goes along with the observed difference image source from the image. In Data Preview 2, there are 8.1 million of these. So we've got 8.1 million DIA sources that match the ephemeris position of a Minor Planet Center orbit and are likely observations of those asteroids. There's about 400 million total observations in the MPC catalog. So this DP2 represents about 2% of all asteroid data ever taken. That's just 20% of a year's worth of data. So it's pretty great. Whole lot of data. And we're currently submitting these associations to the Minor Planet Center, but they're not there yet. Second part of the DP2 solar system pipelines is fitting per object parameters. So for each of these objects that Rubin's observed, for each object that has SS sources, we collect the summary statistics of those SS sources and fit some object parameters. So in each band that an object has been observed, we fit an absolute magnitude. For DP2, we, as Mario said, fixed the phase slope because things really ran away when we didn't fix the phase slope. But we've got errors on absolute magnitude, covariance between all the different photometric properties, which is really just one photometric property at the moment, and a chi-squared. So the chi-squared is, or chi-squared is really really useful in this case because objects have variability. Asteroids are not the same brightness all the time. And when an asteroid whose associations you believe has its photometry not fit the absolute magnitude and phase slope model well, that's a sign that the object, its variability is being measured by Rubin pretty well, that you can get interesting information about the object's shape and light curve amplitude out of our photometry. We also have summary statistics for each object, the number of observations in each band, the phase angle coverage of each band, and the observational arc. We've got 300,000 asteroids out of the 1.5 million known by the Minor Planet Center observed at least once. So in Data Preview 2, Rubin observed about 20% of the solar system. For 170,000-ish, we've got colors, G minus R color or R minus I. More on the colors and their trustworthiness later. All right, those are the pipelines. That's how we generated things. Let's dig into the data sets. SDM schemas is your friend when you use DP2 and want to know how to use DP2. This is a website that very nicely presents the columns of every table, a description of each column of every table, and the units for every column for every table. I really strongly recommend whenever you're digging into the data that you go to sdmschemas.lsst.io and have that up in another tab as you try to use the data. There are schemas for every table that we produce, and the pipelines force the tables we produce to match the schemas. So it's very trustworthy. First, the dia sources, the precursor data product to the solar system sources. These are measurements of a source in an image. So we've got the astrometry, RA, DEC, X, Y, and pixel coordinates, and their errors and covariances. We've got PSF flux and errors on PSF flux, plus template flux, so the flux of the object in the template if it's there, and the flux in the science image. These can be useful if you are wondering whether an object is a stationary source that happens to be associated to an asteroid or a moving object. Importantly, we don't have a magnitude column. We do everything in the pipelines in Flux. You have AstroPy units in the AstroPy table columns, so it should be very, very easy to convert between PSF flux and AB magnitude, but users do have to do that themselves. So get ready to get familiar with Nanogenskis. That's just how it is. The dia sources have shape information and real bogus, which you might have heard about in the previous session here. Real bogus scores, reliability scores. Almost every single asteroid in DP2, almost every source of every asteroid in DP2 has a reliability score over 0.75, and most dia sources in DP2, I believe, have reliability scores less than 0.75. So if you filter on reliability over 0.75, you're going to be very safe for asteroid science. I recommend doing it. There are all sorts of flags that tell you about the earlier pipeline's behavior, and dia sources will have SS object ID, the solar system object ID, set to 0 if they are not known to be asteroidal, if they're not associated with an SS source. They will have dia source, SS object ID greater than 0 if they are associated to an asteroid. The SS source table is not one-to-one, but maps every SS source to a dia source, and you can map them together with the dia source ID column. SS sources have the source information that is only meaningful for solar system object sources. The SS source table does not include the previous data for dia sources. So if you want astrometry or photometry, you're going to have to join dia sources and SS sources together. SS source does have object's minor planet center designation, SS object ID, all of the ephemeris information, including positions, rates, magnitudes, offsets, and state vectors, both heliocentric and topocentric. And it can be joined to the DiaSource table with DiaSource ID, or joined to the SS object table with SS object ID. As previously described, the SS object table is a summary of each object detected by Rubin, each object for which there are SS sources. We've got observation arcs, number of observations per band, phase coverage, per band absolute magnitudes and phase slopes, and all of that, all of the downstream information of that. And it can be joined to both the DiaSource and the SS source. That should be SS source on the left tables with SS object ID. It can be joined to the orbital information with designation column, which is the MPC unpacked designation. And then finally, the MPC orbits table is just us passing on the minor planet center table that we used to create the ephemerides that we associated for SS source association. We did not change the table at all, except to add the designation column. It is the minor planet center table is mostly kept in one giant column called MPC or JSON-B, which is a JSON blob. It is a bit difficult to interact with, but I recommend getting cometary elements, QEI, omega, and pericenter time, directly out of this table. You can try to dig into the JSON blob, but it is a big blob. And please, please, please note that semi-major axis and mean anomaly, so the classical Keplerian elements, are not always set in the minor planet center orbits table. We are passing on the data set that we got from them directly as it is. What we had, cometary elements from MPC orbits are your friend. This table can be joined to SS object on the designation column. A refresher on the joins. This will be important. DiaSource and SS source can be joined with DiaSource ID. They can both be joined to SS object with SS object ID, and the orbits and the photometric information with the designation column. You will probably want SS object for most things you do, and it sort of holds the whole thing together.
There'll be a quiz at the end.
We additionally have submitted a whole lot of data to the Minor Planet Center. So every time we think we've discovered something, we send that to them. They are a public group. Data that they have is world public. And so you can go to b612.ai, go to the data products tab, and download all of the Rubin MPC submissions. This doesn't have all of the columns that DP2 does, just time, astrometry, photometry, but it does have a whole lot of our data in one place, pretty easy to grab, and it is world public, so you don't need data rights to access a whole lot of our photometry and astrometry. Currently, we've only submitted discovery data, not associations, but we're working on starting the DP2 associations today. But Minor Planet Center has their own rules, like ideally they don't want single detections on a night, and so it might take a lot longer for our singletons to get into the MPC database than the tracklets. The 20,000 asteroids that we discovered after DP2 processing in the DiaSources are only going to be available through the Minor Planet Center database, not through DP2, because they weren't known at the time DP2 was processed. Okay, that's the DP2 data sets. Let's take a really quick look into the data and then talk about how you can get it and use it. These were stolen from Mario's slides. We see tens of observations from most DP2 solar system objects. Most of these were observed over periods of ish. There are some serious outliers, some whole bunch of objects detected only once, and a whole bunch that live in deep drilling fields and have many, many months of observation. Our astrometry is really good. So on the left, I think also stolen from Mario's slides, a scatter plot of our astrometric residuals, ephemeris position versus measured position. On the right is a heat map, so that the scatter plot, like it saturates out here. We're actually a lot better than that. This is an arc second, so one of our pixels is a fifth of that, and we're way better than a pixel of astrometric scatter here. We're seeing most objects really, really exactly where we expect them. Okay, not exactly where we expect them. There's a 22 milliarcsecond offset in that direction, which after a whole bunch of discussion, as Mario discussed with Minor Planet Center and JPL and other surveys, we think this is the orbit catalogs, not us. This disappears when we refit orbits to only Gaia data and then check our astrometry versus Gaia only orbits. So it seems like it's Rubin and Gaia versus the rest of the world, which is a good place to be. I would take the Gaia side on rest of the world. But this should not matter for most science with DP2. Just be a little aware of it. Okay, colors per objects. So as I said, objects are variable. Asteroids rotate and have light curves, and they're not perfectly spherical. So on the right, we've got a beautiful SDSS plot made by a UW undergrad, go UW, in 2008. Here are different color families of asteroids, very clearly visible in SDSS data. SDSS had simultaneous colors in different bands, or very nearly simultaneous. So when they made two observations of the object, it was at the same point in its rotation curve, unless it rotated really, really fast. Rubin observations of these objects are typically half an hour to days apart. And so we have, our color families are smeared out by the object's variability. If you want to think hard about the colors of objects, you probably should not take the GH and IH measurements from the solar system object table and subtract them to get a G minus I absolute magnitude color. You should probably think very hard about variability and the extra effects changing those things. So as we get more data, people will be able to fit per object light curves, or maybe just think about the overall statistics of these groups' colors. But you don't rely too much on direct object minus or H minus H colors. All right, that's a sense of the data and what you can do with it. Now let's talk about how to get it. B612 is great if you want what's public, but I think if you're here, you must be a data rights holder. You probably like data releases. So let's talk about how to get DP2 data from the Rubin Science platform. One of the tutorial notebooks has very similar tutorial code to this from lsst.rsp. You can get the TAP service. You can create a TAP service and then submit jobs to it and query. Query the data from you can submit your query, get the data back. This works really great. I tested it last night for the DP2 SS object table, which has 300,000 rows. And although the JSON blob column of MPC orbits kills you if you try to touch it, you can get most of the orbit data that you care about, QEI, omega, omega, pericenter time from the MPC orbits table, no problem. So this is my recommendation about how to get per object information out of DP2. The dia source table, if you were paying a tremendous amount of attention to a slide in Mario's pop quiz, how many dia sources in DP2? A billion. It's too many for the TAP to select star from. And a similar situation from the SS source table. You can't get all the dia sources or all of the SS sources directly out of the TAP service. So I made a file that I've been using for my personal science, which is the merged dia source and SS source tables, and placed it in the shared directory on the RSP. I find this extremely convenient. It is just fetching the Rubin DP2 data. It's about 5.4 gigabytes. You can load it very happily in a 32 gigabyte instance on the RSP. And if you want the merged dia source and solar system source data, I recommend you look in that directory. You will notice I am not wearing my observatory hat. This is not an official observatory data product. I did this as a scientist instead of as a pipelines engineer. And so if you use this, please get in touch with me and let's talk about it. But DP2 solar system data is there. All right, conclusions. Those are the tables. That's how to merge them together. You want them, please look at SDM schemas. It has all of the information that will save you from making lots and lots of mistakes that I have made. RSP is at data.lsst.cloud. go there and get DP2. It's really awesome. If you want to look at the DS source and SS source tables merged together, which I'm really going to bet most people do, there's a file over there. And then the Asteroid Institute has the Minor Planet Center data. Got 8.1 million sources in DP2, 300,000 objects. It's really amazing. Filter on just sort of reasonable things, because a couple of our observations aren't reasonable, but the vast majority of them are. If you've got any questions that come to you after the following questions section, please email me over there. But let's open it up for questions and messing around with DP2 now. Thank you.
Fantastic. Thank you, Jake. All right, questions for Jake?
Thanks, Jake. David Trilling. I know why you did this, but I'd like to ask you about your HelioLink assertion of prograde orbits. And how do you feel about making that assertion?
My HelioLink assertion of prograde orbits?
Yeah.
HelioLink does not assert prograde orbits.
You
It
said on
only
the slide that
asserts radial distance and the derivative of radial distance. So
I think you said you, didn't you say you asserted prograde orbits? Did I dream that? I dreamed it. I apologize.
we are, I believe, equally sensitive to prograde and retrograde orbits, except insofar as our cadence might be more sensitive or less sensitive.
Yeah,
But
okay.
both
thank you.
Thanks, Jake. I was a little confused about your statement that you shouldn't use absolute magnitudes for colors. Do you mean like the absolute magnitude estimated from a single visit? Is that?
No, so even like our cadence is a little weird and spiky, and an object might have just one observation in the G band, or it might have 25 observations all from the same night when it had the same rotation phase. And if you look at the difference in, G minus I and I minus the absolute magnitudes of objects, you don't see the color populations as clearly as you do with simultaneous colors. So that gives the rotational variability induces systematics that we do not measure yet. And if you want to think about the colors of objects, you need to think about the variability of those objects as well. So I'm not saying don't use the absolute magnitudes, but the G.
Does the rotation not fall out with the phase function fit?
The rotation would fall out if we only were looking at objects that had been observed on many different nights with a pretty even smattering of observations across a lot of nights.
Okay.
While that will be true for wide, fast, deep discoveries after the first couple of years, we're not in that mode. Like there's all these deep drilling fields, there's all this random spotty cadence, and you like a lot of nice things. Any assumption you have about the cadence will be wrong for a lot of the objects. Like the cadence is so non-homogeneous across the area that it's a little tricky to do colors well.
Okay, that's interesting. Maybe we can talk about it.
I think people should try to do colors, but think about variability when you do the colors. And assumptions like it'll all wash out don't appear to be true. I don't see color families here.
Maybe another way of thinking about this is, nominally an object may have 20 observations, but they may be 20 back-to-back R-band observations, followed by an hour of wait time, followed by 20 G-band G-band observations. So you might think if those were not stacked one after each other, that they'd average out and the R-band minus G-band absolute magnitude will make sense. But given the cadence, that may not be true all the time. And you might be seeing something that's an artifact of the light curve. So I think we're just trying to warn everyone, you have to judge each object on an individual basis when you're trying to figure out if you trust its color or not. You should look at its light curve and see where the color came from. More questions for Jake?
Mario, there's a couple online and on Zoom and on Slack.
Sorry, my conference.
Is it allowed to unmute and ask a question?
Oh, yes, go ahead. Yes, please.
Hi, Mario. It's Brett Gladman. Hi, Jake. Coming back to the point that Meg made about the cadence, I think it's important when talking to the wider community outside the solar system collaboration to be a little careful about using the word discovery and touting the TNOs, because with this slide up, as you know, those 30-day orbits are pretty meaningless for outer solar system objects. And so it's going to be very important that there's multi-year follow-up. And so the things that are found during this first year of observations need dense coverage the following year to make sure they all get retrieved. And if one says there's this many discoveries and other people say, so you've got what you need, I think it's important to front load the uncertainty of the orbital fits for outer solar system objects.
That's a good point. I think it's fair to say, we're using the definition of discovery, kind of the Minor Planet Center does. And if an object has been seen over multiple nights with multiple observations in each night, and so on and so on. But your point is well taken, that the fact that we may have discovered in that sense a TNO, and it's unlikely that we're going to lose it, but it doesn't mean that we have all we need to do the science with it. And we'll need observations in a year from now, the next year, and so forth to understand really what the precise orbital elements are. So I think that's a good point, something we should keep repeating to, especially folks not in this community, so that it doesn't seem like in 3 years we're done. We're not. I think there were more questions on Slack, but I don't have a Slack in front of me. If somebody else has a question and you want to unmute, go ahead right now.
Meg told me to unmute and ask next. So this is Lynn Jones. I was just wanted to clarify. Jake said that something that I think means that every SS source has a DIA source in DP2. Is that correct?
Yes, every SS source has a DIA source ID. The DIA source IDs are all different, and DIA sources that are associated to an SS source aren't also associated to other things. So yeah, if you have been assigned,
So that means that this is only in the ecliptic part of DP2 where the coads were, right?
Sorry, I couldn't quite hear, but I don't think there's any on-sky position like asterisk on this. I think in the ecliptic or off the ecliptic, the DIA source to SS source map is every SS source has a DIA source.
Right. Okay. Sorry. Specifically, I'm just saying, like, there's not DIA sources over all of the DP2 footprint, correct? So that does mean something about where the SS sources are, as far as
there are. Oh yeah. So Mario had a slide which I was planning to steal, but then decided not to. That shows where the SS sources live, and they're almost all in the ecliptic. Like almost every SS source is pretty close to the ecliptic. A couple, you get an NEO really far south, really far north, but yeah, the SS sources live almost entirely on the ecliptic, but can occasionally be elsewhere. But they're only where we have DIA sources.
Yeah, basically where we have templates where we can get different images.
Yeah, I was just confused because it gets a little complicated because you have the other discovery search, which was running in places which wouldn't require templates.
Yeah, so we have discoveries, we have data in the Minor Planet Center that is not DP2 SS sources. And that's where I think you have to start thinking about SS sources at the release only thing. Like it's just the data product. SS source is it's not the idea of any solar system associated source. It's the DIA sources in DP2 that are associated to solar system objects.
Yeah.
But yeah, we have a lot of MPC transient sources that are not going to be represented anywhere in DP2.
Yeah, and life gets a lot simpler at DR1, right? So, okay, thanks.
Right, so we're almost out of time. We have time maybe for one more final question. Okay, if there are no questions, just a couple of announcements at the end for me. So thank you for coming to this first solar system session. There's going to be another one tomorrow. with a lot more that focus on science. I hope that you've heard enough to start going through the data sets and use these next couple of days to do that. Try things out. If something's unclear, something uncertain, find Jake, find myself, find anyone here from Rubin. We'll try to help you out. But really, the next challenge is let's start going through the data and getting the science out. So I also want to thank everyone in the science collaborations who has helped to get us to here, especially Meg Schwamp, who's, I think it's 1 a.m. at this point in Belfast, who was organized all of you over the last year or so to help us make this a reality. And I think now's the time to take advantage of all the fruits that has yielded. So thanks everyone again, and we're done for today. See you tomorrow.
Thank you, Mario. I just want to announce there's a group photo, so we encourage everybody to participate. When you exit this building, you hang a right, you go up through the green to the fountain, please. For the group photo, it'll be in about 10 minutes, so please do go ahead. And remember, there's a reception at 6 in the other building where Trinity is. Thank you.